as designed, here to talk about continual learning is my lab mate, Cédric. So Cédric is a postdoc at MIT working with Josh Tannenbaum and Jacob Andreas. He previously completed his PhD in Brea, where he worked on recommended accelerator. And so we're excited to hear all about this.
Cool, thank you. I don't really know how to use a mic, so if at some point I turn my face and you don't hear me anymore, just tell me. All right. Hi, yeah. So it feels like today's main question is basically how should we ask robots to do stuff? And of course, I'm going to say a word about that, but I think that I want to take a slightly complementary perspective and defend that general purpose robots should not only pursue our goals, but that they should also learn to represent and pursue their own goals, so that it should be autotelic. And hopefully, as they do their own self-directed exploration of the world, they will also get better at achieving our goals too. Okay. So the first question is why should we have robots that achieve their own goals? And I'm going to offer two different motivations for that. The first one is going to be more scientific, and the second one more practical. The first one is that I'm interested in modeling the open-ended developments and learning trajectories of humans. And we know from developmental psychology that human skill acquisition and learning is really developmental in the sense that we build over the skills that we've already acquired to learn new skills. And it's also very self-directed. We seem to know what to learn, when to learn it, from whom to learn it. And we kind of get out there, go gather the data and the practice that we need to achieve our learning goals. So in childhood, this follows some like relatively predictable sequence of pseudo stages. But after that, we start representing our own goals and pursuing our own goals. And this is where the trajectories of humans really diverge. And so I'm interested in uncovering kind of the fundamental mechanisms that underlie this open-ended learning. And it connects to this definition of intelligence by McCarthy, who coined the term AI, when he said that intelligence is the computational part of the ability to achieve goals in the world. I got that from your paper. And I think it's true that as you're able to represent more diverse and more complex goals, you kind of gain more agency and more control over your environments. And so you gain more capacity for adaptation. And if you're beyond that, also able to imagine your own goals, like beyond the one that nature gave you, then you get better at, you're more creative, you get better at innovation, and also better at just exploring the space of all possible behaviors. And all of those are very key elements of ecological success for humans. The second reason is more practical, is that we might want to build general purpose robots. And so that means that we need to generalize to a huge diversity of goals and adapt to a huge diversity of domains. And the robots that we have for now, they mainly do a few tasks in a few domains. And there's like this idea that maybe you could just pre-train a robot in a factory and hopefully they just deploy it, then deploy your static robots and hope they will generalize to all those goals and domains. I think that's probably not true. And if you want to really be able to adapt to all those goals and domains, it's not only that it's a big space, it's also that you have a huge uncertainty about which goals and domains the robot will face. So if you want that, you need robots that continuously and autonomously learn. And that will mean that they will have to generate their own learning signals, their own reward functions, build their own curriculum towards the hardest goals and so on. And so they will need to be autotelic. So taking a step back, what does it mean for a robot to have a goal? In psychology, people talk about a goal as a cognitive representation of a future object that the organism is going to commit to approach or to avoid. And so we can translate that into machine learning terms, maybe some reward function that measures progress or achievement of the goal, and some goal embedding, which is like the cognitive representation here that points towards the goal. So you can condition your policy on this goal embedding and then use the reward function as feedback. And I'm making an underlying assumption here, which is the reward hypothesis. I'm not going to talk much more about that. It was presented earlier. I'm just going to assume that for a large set of goals, it's holding, and so we can roll with that. And so people have considered a diversity of such goal representations. Sometimes it's just like a point in observation space. Sometimes It's maybe a set of binary predicates that you want to be true. Sometimes it's a linguistic statement that you want to be true about the world. So all of those different goals, and they are also expressed in a diversity of modalities. Can be more visual, auditory, or more abstract, linguistics, and so on. And so far, I don't think it's clear that there will be like a single goal representation that can kind of encompass all that diversity of things that we call goals, or whether we're going to have like goal modules, basically, that will be able to communicate to each other. So now about this autotelic term, it comes from the Greek auto, which means self, and telos, which means the end or the goal. And so it's simply an agent that is intrinsically motivated to learn to represent, generate, pursue, and master their own goals. So if you compare it to a standard reinforcement learning agent that acts, receives states, and that receives its goals and rewards from some external source, usually an engineer, here the agent has to generate their own goals and rewards. And this is how they get really autonomous. And as they interact with the world, they will kind of grow along their life a repertoire of skills, which are just a set of goal representations and the associated goal-directed behavior. And I guess one objective here could be that this process of skill accumulation becomes kind of autocatalytic or open-ended, we could say, in the sense that the more skills you have, and the better you're going to get at reaching more diverse and more complex goals. All right, so now I'm going to go over like a couple of ingredients that we need to build such autotelic agents. The first one is that we need agents that can practice many skills in parallel and can learn to transfer efficiently across them. So we can maybe do that by having like goal condition neural policies that will share representations across goals within their network. We can combine that with a form of inside experience replay, which is basically a counterfactual learning approach that tries to squeeze as much information as possible from every trajectory. And the combination of that and so those two give more transfer and so more faster learning, hopefully. And so we can look at that in a robotic manipulation domain where we bundle together 4 different types of goal manipulations. So you have like a reaching task, pushing blocks, pick and place blocks, and stacking blocks. And there we train a single agent, a single policy to achieve all of those goals in parallel. Also doing like some counterfactual learning across those goal representations. And that's the blue line here. We see that it learns basically much faster than if you were to train independent policies in each of those goal types without any kind of communication. So the bottom line here is that as you represent more goals, you have more possibility for transfers across them. And you also like kind of shape the reward to us because there are easy goals that you can achieve now and train your presentation on. You also get better at exploration, basically. The second ingredient is that you need to let agents select their own goals. If you think of really large representation of goal spaces, they're going to be full of goals that are completely impossible for the agents. Maybe because they are physically impossible, maybe because the agent is not that good enough for now. Also full of like trivial goals. And you have only like one limited lifetime. So you need to decide to prioritize what to practice at any given point. So you can see that as an optimization problem, where the goal is to optimize for an optimal, find the optimal goal selection policy that will maximize your kind of expected performance over all possible goals that you might care about, like extrinsic goals maybe. And this over the whole lifetime of the agent. So if you do any kind of optimization, you realize that it's a really hard optimization problem because you get only one feedback per life. So you need some kind of outer loop evolutionary meta-learning process to optimize for that. But what researchers came up with, it's also what natural evolution came up with, is the idea of using more proximal objectives that are can be optimized by the agent during its lifetime, and that hopefully will correlate well with the two objectives. And in practice, these take the form of intrinsic motivations. You can have agents that focus on goals where that have intermediate difficulty, or goals that are more novel, goals where they progress the most. And the commonality between those is that the intrinsic motivations are constantly redefined as a function of the agent's current experience, or current capabilities, let's say. And so it's going to like shift the objective of what the goals, which goals the agent focus on, and organize, drive basically the learning trajectory of the agent. We can go back to the robotic domain. Here we gave it an intrinsic motivation towards learning progress. And so for that, the agent needs to have some kind of self-knowledge. So in practice, we're going to have it track its own competence. So it's kind of average success rate in each of the goal types. It's going to track also the learning progress, which are derivative of those curves. So learning progress or competence progress. And then it's going to use a kind of Bennett algorithm to sample goals that are preferentially that have the highest learning progress. So we can see how that plays out. It makes progress on the easiest reaching task. Learning progress increases. The interest of the agent increases. It starts sampling them more. And so quickly it reaches mastery there. Learning progress is going to drop. Interest is going to drop. And it's going to start focusing on a second task where it's making progress, which is here the pushing task. So you can see how that plays out. Basically, the agent is going to shift its focus from simpler to harder tasks as it learns. And this is going to organize some kind of curriculum automatically for the agent. So if you take a step back here, for now, we had the goal condition agents that has goals that we give to them. Some goal representations and reward functions that we also give. We give everything. It's just a normal reinforcement learning agent. The curriculum learning variant is just learning to sample those goal space, but it still relies on some hand-coded representations of goals and rewards. But you can see already how playing this kind of agent in a large goal space, and if you give a lot of compute to the agent, such as it can achieve some of those goals, you can already have some really developmental trajectory and manages to reach really high, really difficult goals. And we've seen that in a couple of different approaches in POET, for example, from Uber AI Labs, Ada from DeepMind, and so on. But it's still you're still going to be only able to represent goals that are kind of bounded by the first goal representations that you gave to the agents. And if you want something really open-ended, you're going to need the third ingredient, which is to constantly evolve the goal representations and the associated reward functions. So now we're going to go over a couple of ideas of how this could be implemented in practice. The first one is that we can reuse unsupervised learning methods that learn state or trajectory representations. And once you have those, you can basically use them as goal representations. So people have done that usually in the context of visual observations, where it's too hard to just set a point in visual space because it's too high dimensional and unstructured. So you can't really set a goal there. But what you can do is to use the visual data you collect here, those points, to fit a generative model, maybe a VAE. And once you have that, you can consider the latent space to be your goal representations. So now you can sample the goal in latent space, you can decode it into a target image that you want to achieve, maybe. The problem with that is that you're only fitting your past experience. And so the goals that you're going to sample are also going to be within the type of things that you already experienced. It's not going to really drive your exploration. It's not going to ask you to do anything new. So one thing that you can do that's pretty simple is just to upsample the observations that are in low density areas. And in practice, when you train a generative model, it's just going to give it some bias towards novelty, to focus on generating goals that are a bit novel, a bit different from everything else. And so in this approach, there is all the ingredients. You have a constantly evolving goal representations thanks to the autoencoder. You also have new reward functions here. I didn't mention that yet, but the reward here is the similarity between your latent goal, which is in latent space, and the latent embedding of your current state. So you can get some distance measure there. And you also always evolving the way you sample because it's the novelty intrinsic motivation here. All right. A second thing that you can do is to use social feedback, to use social learning. And I think goal representations, if you need to evolve goal representations within an agent, you need some social feedback such that they become more aligned with what people represent as goals. So in this set of experiments, the imaging agent here is helped by some kind of social partner here simulated one that describes in a simple language whenever the agent does something interesting. So whenever maybe it goes somewhere, maybe it grasps an object or it feeds an object with supplies, like food or water. It receives a description of that. And so in the first phase, the job of the agent is to internalize those representations to make it their own goal representations. So the first thing that you can do is just store the descriptions that you've heard and the trajectory that are associated with that. And then you can later on just resample those descriptions and use them as goals, maybe. The second thing, a bit more interesting, is that you can learn a reward function from those. You can learn kind of a binary classifier that learns to recognize whenever a description describes well a trajectory. Once you have those goal representations, then you can move on to a second phase, which is more exploratory. Here, the social partner is not there anymore. And we gave it some kind of symbolic generality model that would like take the description that it has heard and kind of recombine them in different ways. And the way you do that, then, I mean, when you do that, you kind of get some new goals, so imagined goals in that case. And now we can condition the policy on those goals and let the agent go explore condition on those goals. But more interestingly, what you can do is that you can rely on the generalization capabilities of the reward function. So instead of just following the goals and trying to achieve them, you can also compute rewards towards them and then kind of train autonomously towards them. So now exploration is not only about adding some noise on the policy or maybe optimizing for some perceptual novelty. Now exploration is about imagining your own goals and then actually committing to them, going in the world, explore towards them and training towards them. So here it's a pretty simple environment. So imagine only simple goals. Imagine that it can feed plants. That was never said by the social partner. It can try to do that. It can get better at doing that also with its own learning signals. And then he imagines they could feed furniture as well. And in that case, it doesn't work. You cannot really like feed a door with Apple. But I would argue that when you look at the agent doing that and exploring in this way, you still kind of endow it with some form of agency. It still looks like it's committing to something and trying to achieve something. And it's a much more like structured exploration mechanism, I would say. And that's because the goal that it imagines and pursues is kind of expressed in the same language that we express our own goals. And so it looks more human in that way. Okay, now a third idea. So in the previous one, we used the language to represent more abstract and time-extended goals. And so we can push that and say, maybe we can reuse the pre-trained representations of large language models as goal representations and kind of leverage their ability and then sense of common sense to guide the sampling of goals. Because the one limitation of intrinsic motivations alone is that if you imagine that anything could be a goal, right? You're in the real world, anything could be a goal. Then there's kind of an infinite amount of goals that would be novel, infinite amount of goals where you could be making progress. So you need some other way to further constrain the goal generation. And here humans have like other constraints. So we would have goals that use objects that are around, so that are more like context sensitive. We would set up goals that respects the laws of physics, that respect social norms, that would be like plausibly useful for later achievements that we want to have. So we need to like embed this kind of common sense and human intuitive notion of what's interesting and relevant, in addition with the intrinsic motivations to guide the goal selection. So we looked at whether we could do that with language models. It was one project led by collaborators at Berkeley and one in collaboration with people at INRIA and Microsoft. So in this one, we have like a 2D version of Minecraft that's called Crafter. We can turn the states into language, and then we can ask the language model, what should I do next? We see a bunch of goals here. The interesting things to note are that they are kind of diverse, not the same twice. They respect physics. You would like eat a cow or cut down the tree. You would never like build a cow or drink a tree or this kind of weird stuff that other models could invent. And they're also context sensitive in the sense that they suggest goals that are relevant to the actual current state of the agent and the current inventory. So it's a way of like incorporating some kind of loose common sense in the goal generation. And once you have that, you can like further prompt the language models to also integrate some form of intrinsic motivations. So what you need to do basically, I mean, the assumption here is that language models have these universal representations where potentially any kind of goals could be expressed. So your job is to like provide the right context to the language model such that you focus it on giving the right kind of goals for the agent. So it's already what we've been doing here by providing the immediate like state context to the agent such that it would give like context sensitive elements. But for intrinsic motivation, you need to provide some self-knowledge context to the language model as well. You need to tell the language model which kind of goals you've already experienced, which ones you find currently too difficult, which one you master already, which one you're making progress on, and so on. And if you give this right context, then the language model can shift its recommendations, integrating both the common sense and the intrinsic motivations. One last thing that I didn't mention here is that I've talked about how to generate goal descriptions. But as I've said, the goal representations are not only the embeddings or the description, but also the reward function. So you also need that. You can get that in various ways. One way is like if you can rely on a captioner, then you can kind of measure the similarity between your goal description and the caption of your trajectory, something like that. Or maybe get the likelihood of the goal under the captioner, something like that. And that works pretty well, but you need a good captioner, which is very hard to get. Another thing that you can do is just ask the language model. So you feed the whole trajectory to the model. Maybe it's text, maybe it's like a video, and you need to use like some multimodal model. And you ask whether the goal was reached. It's going to be good in some ways and bad in others, as often. But the interesting thing is that from that, you can also get other outcomes that were achieved in the trajectory. You can ask, so did I achieve the goal? And also, what else did I do? And once you get those labels of other things that you could do, you had achieved, then you can use them basically to do some kind of inside experience replay. So you can learn also more broadly, not only about your current goals, but about other goals. And the last idea is that you can ask the language model to convert those goal description into a Python-based reward function that you can just run on the trajectory at the end. And the good thing is that it makes it much more interpretable. You can look at the code, you can see if there's, you can debug it more easily and so on. All right. So the takeaways here are that general purpose robots must generate their own learning signals if they want to adapt to any kind of goals and domains that they might have to face. And so for that, they're going to need to be autotelic. That autotelic learning is basically made of 3 ingredients, maybe more. The first one is that they need to achieve many skills in parallel and efficiently transfer across them. The second is that they need intrinsic motivation to kind of drive the selection of goals within huge goal spaces and prioritize. And the third one is that they need to also continuously evolve their goal representations as a function of their experience. And so you can get that from unsupervised learning processes. You need also to incorporate some social feedback to align the goal spaces across agents and between agents and humans. And in this idea is also the fact that you can't just rely on intrinsic motivations. You need to integrate also forms of common sense in your goal sampling. All right, the last point is that we still haven't built any kind of truly open-ended system. If we define open-endedness as the endless generation of novel and interesting artifacts, where artifacts can be like robot skills, but also be like artificial creatures or like arts or program problems or something like that. Anything basically. And so we have a lot of interesting diversity producing algorithms. There are like the quality diversity side, the autotelic approach that I presented today, but they all converge pretty fast. Like after maybe a day or like maybe a week, up to a week maybe, they kind of run out of new things that it could generate, like new robot skills or like more complex robot skills. They converge. And so, yeah, to take back this bit from Ken Stanley, it seems that we still haven't found like the necessary and sufficient condition that would like kickstart the open-ended process, because then it would mean that we could run it kind of forever. It would still like continually present new interesting artifacts. And so natural evolution has been running for forever, basically, and still like not plateauing. It's still like generating new interesting things. So we still haven't found those necessary conditions, and there is like much more work to be done. I don't know if I have time to go over these different questions, but they are like the open questions for me. There are many more, I'm sure. So what makes a good goal, an interesting goal, a game fun? So what are like the real interesting motivations behind that? The one I'm especially excited about is like, how do we combine this autotelic learning with ideas from cultural evolution? So how do you evolve goal representations, not only in a way that lets you interact, achieve some goals, so not in an intrinsically motivated direction, but also in kind of as a population, where like your goal representations are influenced by the one of others, and now yours also influences others. All right. Last thing I want to say is that if you're interested in these kind of questions, you should consider joining the intrinsically motivated open-ended learning community, which organizes events and discussions around those questions. We have a workshop at NeurIPS later this year. And yeah, I want to thank all my collaborators on the projects and ideas that are presented today. And I'd like to thank you for your attention. Thank you.
Thank you, Cédric. And we have some time. We started late on this one, so we have some time for questions. I was curious about this representation. Different representations maybe the same will have different group, but also for us as designers. I was curious whether you think about the representation, right? More aspect of the problems kind of design, actually understand.
Yeah. Thanks. Good question. Yeah, so I think, I think about that problem as you need kind of the reward function, the unambiguous thing that defines what the robot is trying to achieve. And then the goal representation is more to like help the robot relate that goal to other goals that it has seen, or like decompose it into sub goals. So it's like giving cues of how to achieve that goal that you wouldn't get from like, let's say, a neural reward functions that doesn't give you any information, right? So it's more like like kind of cues to like learn how to achieve the goal. And I think the second part of the question is like, how does that relate to how people ask a robot what to do something? Sorry. And so I think of that as like, there are inner representation of what are goals within the robot, and the designer or the person instructing it doesn't need to know that and shouldn't have to know that because it's very complicated probably. So instead, what other people, when you instruct, you would like describe, you would give a demonstration, you would give an example maybe. And the job of the robot is kind of to do inference over that. It's like, what would be the goal that they would have in their minds that would lead them to generate those cues to me? And then you need to do this kind of Bayesian inference of like, so what is the goal representation that I should represent for that goal? And I think, yeah, that's how we solve like the communication thing, I think.
Any other questions? Maybe I'll ask one. So coming from a robotics background, I was wondering, your line of work, how do we extend to like on the real robots, where the action space of and the observation space are more complex?
Yeah. Yeah, there are two components. There is like, I'm mostly interested in how you represent goals, but then obviously if you want to have these like co-evolution of goal representations and goal like behaviors, goal-related behaviors, you also need like the goal-related behaviors to like catch up, right? You can't just be imagining goals and then have the agent do nothing. So yeah, I guess nowadays like it's easier to imagine goals than to reach them. So we need to make kind of progress on that dimension. And the other thing that I want to say is that there's this like vision from, I've heard George Konidaris talk about that a lot, that if you want to be like truly general purpose, you need to have very low level sensors, very low level representations, because for some tasks you might have to like do really fine things. But if you want to solve very like abstract problems, then you need to have this way of abstracting away from the low level sensors into a high level representation. that is easier to search in. And so I feel like we still haven't solved like this problem of how do you condition on the goal, kind of generate on the fly the right action and state representations. And I think that's probably the thing that we need to solve first, if you want to like connect those two.
Thanks so much. Any other questions? If not, yes.
I have a question, but I want to ask the panel because I want, so I'm open.
Okay.
You just put them about this case about this. Do you think there is an algorithm that we should run for a billion years?
Yeah, I think we haven't found it. Yeah, I think we just haven't found it, but I mean, it's basically like when you think of like the scientific process, it's something that I want to see running forward forever. And so there are like stuff like that, that if we could get there, if we could have like a purely robotic AI scientific process that would give us like infinite technology, then yes, sure. But then, yeah, you need to still like connect it to our problems. I mean, it needs to like be interesting. So in open-endedness, there's the novelty, and then there's a learnable and interesting. And so it needs to be interesting to us, such that I want it to run forever. And so that's why I think it needs to be, I mean, whatever it is, it needs to be collected to the human cultural evolution process in some way. It can't be like separated from that, otherwise it's sick.
Okay, thanks so much. And let's give another round of applause to